All right, we should be all set to go here. What's up, guys? How's it going? So today we're going to talk about day 2 and day 3 of my summer nuclear physics research project. And so I'm going to start off. The reason I did this on Zoom today instead of on my iPad is because I've mostly just been writing code, um, which has been, you know, really fun in my opinion, but it's not what I'm super hardcore good at. I'm getting better, and that's why I've enjoyed it. But I'm mostly a chalk and chalkboard kind of guy. But you know, Dr. Daniels has kicked me out of the nest, and I'm either gonna fly or fall to my death. So first thing we worked on today, um, or sorry, yesterday, and then early this morning was I had to fix the cross section constant that I had calculated. So one thing that you do in physics when you make calculations, whether it's for homework on a test or in the lab, one of the things you should always do is check units. And so when I was doing my cross section, I had to figure out the cross section constant because I was going to check the uh, cross section at different angles, and in order to do that, I needed to code in a constant in front of the angle component of my cross-section equation. And so the cross-section is calculated here first in meters squared and secondly in barns, which is again a nuclear physics unit. And so the first thing I did was I wrote up the equation. This was on day 1, and I did a unit check, and my units were correct. Um, but I made a little whoopsie because in my unit conversion, uh, I changed the incident alpha particle energy from mega electron volts into joules, and that gave me my correct units of meters squared for my cross section. However, when I actually calculated the numerical constant, I left in the um, MEV unit, so my cross section constant is off, which made my cross-sectional data that I coded up be off by a factor of 1 quintillion. So if you're having a bad day, just remember that I skewed my data by a factor of 10 to the 19. However, I did fix it um, and did the correct calculation here on Python after I did it twice on paper and on chalkboard to make sure I wasn't losing my mind. Um, and so that's what we got here. And so once I was able to get this correct cross section in Barnes, I redid the cross section versus scattering angle plot. And as you can see, this is similar to the plot we talked about in the last video. However, on the y-axis, you can see that the cross section is now on the top end at 10 to the 9 Barnes per steradian, whereas on my other uh, data calculation, which I think I have here, um, I'd already changed it, but the other one was not similar. They were off by a lot, but that's okay. Failure is a part of the game. So once I got that corrected, I was able to just fix up some of the other uh, calculations I had made with that cross-sectional constant. And thankfully, I caught that error because Dr. Daniels was ready to all but abandon the experiment because I was calculating count rates on the order of 10 to the minus 7 per second, which means that we would have had to take data for like, 3 days to be able to detect like 7 alpha particles. So it's a good thing that we got that fixed up. Because then when I did my calculation for the count rate at different angles, you can see now that at an angle of 3 degrees, we're sitting at sorry about that. We're sitting at a little over 2 counts per second, which is great because then if we run data for 60 seconds, we're gonna have hopefully somewhere on the order of 120 alphas, at least incident on our detector, and then depending on what the efficiency of our detectors are, we should calculate at least uh, or detect at least like 85% of those. Um, so, and the efficiency of the detector is something that we're going to have to figure out experimentally. So that's why we're running these simulations, basically to have a theoretical prediction for what our counts should look like. And so this right here uh, was assuming that our source was 15 centimeters away from our collimator, which is going to generate our alpha beam. And this one here is assuming that it's 7.5 centimeters away, which is, I think, the one we're going to go with, because for that one, we're looking at a little over 9 counts per second at 3 degrees. And if we went even closer, we might even be able to get some of the higher angles to be closer to 1 per second. So that's another reason why Dr. Daniels had me code all this stuff up instead of just, calculating by hand, because now that I have all these different constants plugged in, I can kind of play around with different incident rates and see what the counts will be at different angles based on different parameters, like how far the source is from the collimator, what the angles of the collimator are going to be, what the solid angle of the collimator is going to be, which are all things that I calculated um, yesterday. Um, Here we did a calculation for the number of the alphas incidents. So I actually got that. What we had to do was you have to assume that the alpha particles are emitted in 4 pi steradians, which basically just means the surface area of the sphere. And you're basically taking a little, piece of that surface, and that's the section of the sphere that the alpha particles are actually going to go through to get into uh, the collimator and actually hit the foil. So you have to do a calculation where you find the fraction of the alpha particles emitted that'll actually be incident on your foil. And once you figure that out, you can get your incident alphas per second in that solid angle. Because this right here would be how many alpha particles are totally emitted. And then based on that fraction, we gather how many would actually uh, fall into that solid angle subtended by the collimator. And so that really sums up what I did yesterday and this morning. And I'll finish up quickly, just showing you guys some of the cool stuff that I did today. And that would be using this simulator called TRIM, which has to do with how ions travel through uh, layers of mediums. And basically, what we're doing is we're calculating, okay, if I have my tantalum foil and I know the thickness of my tantalum foil, and I know the incident energy of my alpha particles, which is here, and I know things like, the atomic weight of tantalum, all that stuff, you just plug in. It actually does it for you. It's nice. You go and click on the periodic table, and it just generates all those numbers for you. But you do have to figure out, the thickness of your foil and the incident energy, but those are easy to find. And then basically what you do is you run a simulation for how many of those alpha particles will get through, or if they will get through based on the thickness and their incident energy. And then what TRIM does is it compiles the final energy of all of those alpha particles, because when the alpha particles go through the foil, they, lose some of their energy, and we have to know how much energy they're losing on average, because we can't just use the incident energy because that's not correct. And once we figure out the average of their energy after going through the foil, We can use that when we actually do the experiment to know what energy we should be expecting to hit on our detector. And what I'm going to be doing tomorrow is compiling all of that data into a histogram using Python and using the histogram to determine the standard deviations of the energy distribution and the average energy for all those different alpha particles. So I'll just show you what trim does real quick. It's really fun to look at, and then go ahead and call it there. So you just run it, and then out up here it's telling you how many ions gone through the foil. And as you can see, this is the depth of the foil. So as long as they reach the end, then you know that they're all getting through, and there you go. So that right there would be um, how trim works. And so some of the stuff that you see down here is like ones that are scattering off, etc. So cool stuff. Um, all right, guys. I hope you enjoy, and I won't be able to post a video tomorrow because I have to work. Um, also have to work all day Friday and all day Saturday, but tomorrow is the last day I'll be in lab this week. So I'll put a video together on Sunday and I'll do a recap of tomorrow, and then I'll be back again on Monday evening. So, all right. I hope you guys are doing well wherever you are, and see you soon.